Okay, good morning, everybody.
Good morning.
Good morning.
Good morning.
Let's go ahead and get started today. Any questions? Any questions from chapter 10 or chapter 6? Okay. All right, so what I'm going to do today is I'm going to talk a little bit about our next topic, which is quantum mechanics, chapter 6. We've talked about the waves, the idea of waves with electromagnetic waves. We've talked about the electronic structure of the hydrogen atom. And we've talked about the de Broglie matter wave equation. So where we're at right now is we're trying to gain some insights, some understanding of electrons in atoms. As you know, when we talked about redox chemistry, chemical reactions often involve the transfer of electrons from one reactant to another. So to gain an understanding, a deeper understanding of chemical reactions, what we want to do is we want to talk about these electrons. What are they? How do they behave? How do they transfer from one atom to another or from one molecule to another? And so in order to do that, we have to understand the properties of electrons. And what we talked about yesterday is that it is sometimes convenient to think of an electron as a little dot, as a little particle. That can be a very convenient way to think of them. But there are properties of electrons that don't obey that type of physics. They actually behave more like waves. So that's what essentially de Broglie showed through his equation, is that we often have to treat electrons as waves. So we'll get into that a little bit more today. But another aspect of it has to do with the idea of measurement, which is how well can we make measurements? And so this is section 6.5. And this is what's called the Heisenberg Uncertainty Principle. Okay, and what we would claim is that the electron, because it is a subatomic particle, because it is small and has wave-like properties as well, it obeys this Heisenberg uncertainty principle. And essentially what this says is the following. Our knowledge of subatomic particles is limited intrinsically. I put an extra I in there. I don't think that's how you spell intrinsically. Doesn't look right either, but it's close enough. Inherently would be another word to use for that, meaning that because they are subatomic particles, what we can know about them is limited. And what I mean by that is that when we look at a physics problem involving a rocket, we can very, very accurately and very, very precisely calculate the position of a rocket, the speed of a rocket, the acceleration of a rocket, very, very accurately and precisely. With subatomic particles, we cannot do that. There are limits to how well we can know certain variables about them. And so the two variables I'm going to talk about for the electron are velocity and position. Okay, so velocity is how fast something is moving, right? How fast an object is moving. We all know that. And position is the location of an object. Okay, and so here's the principle in a sort of qualitative way. Imagine you have this particle that is moving in the x direction. Okay, so it's moving to the right. This is what we would call the x direction. And I want to measure where it's at and how fast it's moving. In order to do that, I have to interact with the particle. So one way that I could interact with the particle is I could put a little light source here. So let's say this is the sun. So it's a light source, right? And then I could put my eyes right here. And what I'll do is I'll use the sunlight, the photons coming from the sun, to bounce off the object. Some of that light will go into my eyeball, and then I'll use that information to determine how fast it's moving and where it is. That's what we do, right? That's as animals with eyesight, with vision, that's how we determine how to survive, right? If a bus is coming and you see that it's coming, you don't run out into the street. But if it looks like it's far away and it's moving slowly, you cross the street, all right? So the issue here is that works very, very well if we're talking about a bus and a person, because we're in the macroscopic world. But at the atomic level or the subatomic level, there's a problem. And the problem is because the particle is very small, let's say it's an electron, the electron has a very small mass. (10 to the minus 31, well, almost 10 to the minus 30 kilograms. That's a tiny mass. So what happens is if one photon strikes, that's the limit, right? You can't have less than one photon, can't have half a photon. If one photon strikes the electron and bounces off of it into my eye, it's not clear I could detect that electron with one photon, but suppose that it did that. The problem is the photon itself has what we call momentum. Now, momentum for a particle is the mass of the particle times its speed. I guess I'll use a U for speed. Okay, that's the momentum. So the more mass something has, if it's moving, the more momentum it has. The faster it's moving, the more momentum it has. So what happens is when you have a collision, is the moving object, let's say one object is moving and the other one is not, the other one's stationary. The moving object has momentum because it's moving and it has mass. When it strikes the stationary particle, it transfers in that collision some momentum to the stationary particle, and now the stationary particle starts to move. So there's a transfer of momentum. So the same is true for a photon. A photon also has momentum. We said that the wavelength of a photon, we said that the, I'm not going to actually go for the equation there. So the photon also has momentum. Okay. And so what happens is when that collision occurs, there's a transfer of momentum to the electron. And so what does that do? It changes the electron. So now we have a collision. And so now the path of this electron has changed. It might go faster, it might speed up, or it might change its position. It might move over here. And that's not something that we worry about when we look at a bus coming across the street. We don't worry that by looking at the bus, that is somehow going to change the speed or the position of the bus. Because the bus is so massive, photons are unable to affect its speed or its position. But that's not true for an electron or any subatomic particle. When you actually observe, here's the key word we use, observe. When you observe an electron, you affect the electron dramatically. You change its speed and or its position. Okay, so what that means is just by observing something, you have changed it. And that is called the Heisenberg Uncertainty Principle. It says that just by observing an object, you change the object. So you cannot know things about the object just sort of like I know about it. By trying to measure it, you're actually changing it. So it's no longer what it was before. And that puts some very serious limits in terms of what we can know about the electron. If we have an atom with a nucleus and we want to know where that electron is, the only way that we can tell is by shining photons on it. But by shining photons on it, we're changing the electron. We're moving it or making it go faster. So what that leads to is uncertainty, which means we don't know. We don't know where it is, and we don't know how fast it's moving. So what Heisenberg was able to do was to quantify this. He was able to develop an equation through a mathematics that we certainly won't go through. And the equation looks something like this. Delta P times delta X is greater than or equal to H over 4 pi. Okay, so this is the Heisenberg uncertainty principle in equation form. Okay, so let's define these things. Delta P is called the uncertainty in momentum. Okay, delta X is called the uncertainty in position. H is Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. And then 4 pi is just 4 times 3.1415, however many figures you want to put in there, right? Pi is an irrational number, doesn't have an ending. That's 4 pi. So let's talk a little bit about uncertainty of momentum. Oops. So momentum is P, the symbol P, is equal to the mass times the velocity, right? This is just mass and then velocity, speed. So the uncertainty in principle is the mass times the uncertainty in the speed. So the mass that we're talking about is the electron. So this is the mass of the electron. And we know that value. That we know. 9.109 times 10 to the minus 31 kilograms. Okay. So what this says is that this uncertainty multiplied by this uncertainty cannot be less than this constant. This is just a constant because H is a constant, 4 is a constant, and pi is a constant. It's got to be at least equal to, but greater than most likely this constant right here. So what that means is it can't be 0. And what that's telling us is that we cannot know the velocity and we cannot know the position perfectly. There's going to be some error, some unknown quantity for those two values. Neither one of them can be 0. Because if either one of them were 0, that would give you 0 on the right side. And that's impossible according to the Heisenberg Uncertainty Principle. Oops. Looks like we lost our little zoom here. Let me open this back up. I've been working this iPad pretty hard. Oops, I'm going to have to change my sharing here. Okay. There we go. Okay. Oops. All right, so let me get this closed now. Oops, there we go. All right, so let's go ahead and take a look at a problem. What I'm going to do is I'm going to show you a problem from Alex, just so you can see how to do this problem here. So in this particular problem, they say that you have an atom of xenon. And then xenon is Xe, right? And it has a radius, which is 108 picometers. Okay. And its speed is equal to 137 meters per second. Okay. So we know its speed and we know its radius. Okay. So then they say, suppose that we measure the speed of the xenon atom to 0.010%. Okay. Calculate the smallest possible length of a box inside which the atom could be located with certainty. Okay. And then we're gonna do another aspect of this question in a moment. We're gonna sort of interpret it in a moment, but let's do this first part here. Okay. So you have an atom. So you have this atom. And the size of the atom is 108 picometers. We're not going to use that first. But imagine this atom is moving, right? Remember with gas phase, gases, the atoms are bouncing around. So this atom is moving and its speed is 137 meters per second, which is a few hundred miles per hour, a little under 300 miles per hour. And we're going to measure this speed, right? So it doesn't say how we measure that speed. Most likely we would use some sort of laser beam, shoot a laser at it and measure the photons coming off of it, kind of like police used if they're doing a speed trap. They'll shoot a laser beam at you, and the time it takes for the laser beam to get back to the gun, that essentially tells you how fast the car is moving. So we can do the same thing with atoms. So we do that and we measure the speed, and it says here the speed is known to 0.010%. That right there is giving you information about the uncertainty in the speed. So what I'm going to do is I'm going to show you how to get the uncertainty in the speed. And we're going to call that delta U. Delta U, what you do is you say, okay, 0.010%. Well, percent 0.010 is a number over 100. Okay. That's what percentage is. You divide something by 100. So it's 0.010 over 100 times the speed. And that's going to give you the uncertainty. So you take the percentage uncertainty. This is percent uncertainty. You divide that by 100, and then you multiply that by the speed. And you're going to get a pretty small uncertainty. You're going to get 137. It's going to be like 0.0137. Let me see, 0.137, I'm sorry, 137 times 0.01 over 100. Oops, I can't do that. 137 divided by 100 divided by 100. Yeah, it's 0.0137 meters per second. So really what they're telling you here, just so you kind of get the idea here, is they're telling you you measure it's going 137 meters per second. You know how fast it's going, but how well do you know that value? Is it 137 exactly, or is it 137 plus or minus 1 or plus or minus 0.1? What they're saying here is it's really plus or minus 0.0137. So you really know that velocity very well. Okay. Now, what that tells us then is because of the Heisenberg Uncertainty Principle, delta P times delta X has got to be greater than or equal to h over 4 pi. This we can calculate very easily. H over 4 pi is very easy. So let's calculate that right now. 6.626 times 10 to the minus 34 joule seconds over 4 times 3.14159. I'll just use, what was that? 6 sig figs there. We don't need to use any more than that. 6.626 times 10 to the minus 34 over 4 over pi. And you get 5.2728 times 10 to the minus 35 joule seconds, right? 4 pi doesn't have any units, so it's just the units of h. So now what I'm going to do is I'm going to take this Heisenberg uncertainty principle and write it this way. Remember, delta P is mass times the uncertainty in the speed, delta U. We know what delta U is. So I'm going to write this as m times delta U times delta X, right? Because it's delta P delta X. So m delta U delta X has got to be greater than or equal to. Now, when you do these calculations, you're just going to do equal sign. Okay, so now take a look at what we know. We know h over 4 pi. We know delta U because we did that calculation right here. We want to find the minimum size of the box. That's what delta X is. This is the minimum size of the box. So imagine it this way. This xenon is moving, and we know its uncertainty and its speed. This is going to be our uncertainty this is going to be the uncertainty in the position, the size of the box, essentially, how long the box is, the length of it. So in order to figure that out, we need to find delta X. We're going to have to divide both sides by the mass and the delta U. So delta X would be this number here. Divided by the mass, divided by the delta U, which is 0.0137 meters per second. So the only thing we don't have is the mass. So now we have to figure out what the mass is, okay? So what I'm going to do is I'm going to show you how to find the mass. It's a xenon atom. So what you do is you look in the periodic table, you look for xenon. Xenon, I think, is element number 54. Grab my periodic table here. Xenon is 54. And the molar mass is 131.3. But we want to know this mass in kilograms per atom. So this is not in kilograms per atom. So we have to figure that out. So here's your conversion. 1 AMU is equal to 1.661 times 10 to the minus 27 kilograms. There's your conversion factor to get it into kilograms. So 131.3 AMU. Remember, AMU is how much one atom weighs. We're trying to figure out the mass of one atom. So times 1.661 times 10 to the minus 31 kilograms divided by an AMU. Okay, that's going to convert it to kilograms. Remember, everything's in MKS for these calculations. So times 1.661 times 10 to the minus, oh, why did I put 31? It's 27. 27. And you get 2.181 times 10 to the minus 25 kilograms. So there's our mass. So now let's come back. We got delta X is going to be greater than or equal to, and that number was 6.626 divided by 4 divided by 3.14159. So 5.2728 times 10 to the minus 35 kilograms over the mass times delta U. 2.181 times 10 to the minus 25 kilograms. Okay. Oh, sorry. Joule seconds. And then 0.0137 meters per second. Okay. So h over 4 pi divided by m divided by delta U. That's going to give us essentially the size of this box. So now we just do that arithmetic. 5.2728 times 10 to the minus 35 divided by 2.181 times 10 to the minus 25 divided by 0.0137, and you get 1.7647 times 10 to the minus 8. Now the units, I got to talk a little bit about the units here. They don't look right. It doesn't look like the kilogram is going to cancel, but it turns out kilograms does cancel. Remember, we want position, uncertainty in position, so that should be in meters. So here's how it works out. The joule is a kilogram meters squared per second squared. So you really have joules times seconds divided by kilograms divided by meters per second. So the kilograms cancel. One of these meters cancels here. One of those meters cancels there, and the other one cancels there, and you get meters. So that is in meters, okay? It just naturally works out from the equation as long as you have the mass in kilograms. So there's our uncertainty in position, okay? All right, so what does that tell us? Well, it's hard to interpret that unless we go further into the question. So the second part of the question says that we know the radius of the xenon atom is 108 picometers, okay? What we want to do is we want to write the uncertainty in the position as a ratio of the size of the atom. The size of the atom, okay? In the radii. Okay, be very careful when you read these. Write your answer as a multiple of the radius, okay? It's very easy to make a mistake on that. And then it says to round it to 2 sig figs, okay? So let me show you what we mean by that. The radius of the xenon atom, that's a measure of how big it is, right? And I'm not going to go through it, how we know the size of an atom, but there are ways to measure the size of an atom. So this is the radius of the xenon. And what they're telling us is it's 108 picometers. So let's do our conversion here. 108 picometers. A pico is 10 to the minus 12. So this is 108 times 10 to the minus 12 meters. So 108 picometers. So there's the radius. So what they want you to do is they want you to take the number that you got here, the size of this box. So, you know, the box length. That's delta x. And they want you to divide it by the radius of the atom. Of course, they have to be in the same units. So that would be 1.7647 times 10 to the minus 8 meters. So that's the uncertainty in the position, divided by the radius, how big the atom is. And there you go, that radius. Of course, it should end up, there should be no units in there. It'd be like if I said, how much bigger is someone who's 8 feet tall compared to someone who's 4 feet tall? It would just be 8 divided by 4, 2. The ratio would be 2. Okay. So 1.7647 times 10 to the minus 8 divided by 108 times 10 to the minus 12. And you get 163.398, but it says to round it to 2 sig figs. So that's 100 and I guess it'd be 160 to 2 sig figs. Okay. 1, 2, or 1.6 times 10 to the 2. And so that's 160 times larger. So what we're saying is this. Now let's come back to the interpretation of this. What they're saying is you measure the size of a xenon atom, and it's 108 times 10 to the minus 12 meters. We then try to measure the speed of the xenon atom, and we measure it all the way out to really well, 0.01%. That's really precise, which is an uncertainty in the speed of 0.0137 meters per second. So we measure how fast it's moving really, really well. But if you come back to the Heisenberg Uncertainty Principle, what that says, this is h over 4 pi. What it says is, this is a constant over here on the right side. This can't change. H can't change, 4 can't change, pi can't change. So that's a constant. So if this gets really, really small, this one's got to get large, right? Like if you multiply two numbers together and they're equal to a constant, if one gets larger, the other one's got to get smaller. So really what they're saying in this problem is they made this really small by measuring the uncertainty in the velocity really well. That means this is going to be really large. And how much larger is it than the size of the atom? It's 160 times larger than the radius of the atom. So that's a lot larger there. So the interpretation would be that you're trying to measure the size of this atom, where it is at least. What we're saying is you don't even have any idea where it is. It's somewhere in a box that's 160 times the size of the radius of the atom. Okay, it's somewhere in that gigantic box. If you want to know where it is closer than that, let's say you want to know it to this size, what you'd have to do is you'd have to say, we got to make this really large so that this one can be small. So if this is really, really large, what you'd be saying is the uncertainty in the velocity is 100% of the velocity itself. In other words, we really don't know how fast it's moving. So if you don't know how fast it's moving, then you can know where the atom is pretty well. Okay. So that's that's kind of an interesting problem. It's a pretty hardcore physics problem for you guys to work on. Take a look at that one. The main thing that you're really doing is you're just manipulating that equation and you're just doing unit conversions. So the mass has to be in kilograms, so convert that to kilograms. Remember, I got the mass from the periodic table in AMU, and then I just multiplied it by that constant here. This is what's going to convert it into kilograms. So once you've converted that into kilograms, then you can use the uncertainty principle. Typically, when you do these problems, you know everything on the right side, that's known. The mass, again, you had to calculate that. And then they're going to give you the velocity as a percentage. So if you remember what I did for that one, let me save that one. What I did for that one was I said, look, you take that percentage, that's the percentage they gave you, divide it by 100, and then multiply it by the speed that they gave you. So they're going to give you the speed, they're going to give you this percentage, multiply those together, that'll give you your delta U. And then you can use this equation here to find delta X, okay? Interesting problem. So what's significant about that for us is that we can not know the position of an electron very well, and we can't know the speed of the electron, or at least we can't know both of them at the same time. So if we're trying to understand the structure of the atom with its nucleus at the center, and we want to know, what is that electron doing? You know, physicists like to do stuff like that, right? We like to find out what things are doing. Engineers like to do that. Biologists like to do that. They, you know, if you're taking a biology course, you're trying to figure out what these molecules are doing, what these atoms are doing, what these electrons are doing. Same with chemists. We would love to know all that too. But what this is saying is, in an atom, we really don't know what this electron wave is doing. We don't have any knowledge of its motion. The uncertainty in its position means that it could be doing this, or it could be doing that. We don't know what it's actually, we don't know what its motion is. In general, we think the motion is more like this, but we really don't know anything about its motion. We don't know how fast it's moving very well, all that kind of stuff. You can actually measure the speeds pretty well, but that gives you no knowledge about the position. Now you just don't know where it is. Okay. In fact, what these show you is that if you have a bunch of atoms, let's say you have a solid, and you do this calculation, this Heisenberg uncertainty principle, what it tells you is that if you're trying to find an electron on this one atom, by doing these measurements, it tells you the electron could be here, you know, anywhere on any of these atoms. So you don't even know which atom it's on. And in fact, that's how electrons behave. They actually will split up in a sense. The wave will spread out over more than one atom. And that's really what a chemical bond is the electron is no longer located on one atom. It's actually spread out across two or more atoms. That's really what a chemical bond is. So it's kind of cool. So let me delete that one. And let's go on to the next topic.
I have a curiosity question. Do we really know that photons affect electrons, or is that sort of a philosophical assumption?
So there were some very interesting experiments they did back in like the 1930s, 20s and 30s, which is called Compton scattering. So what they do is very clever. You take a high energy photon, which is like an X-ray, right? So we have good X-ray technology, right? We have, you know, even in a doctor's office, they've got an X-ray machine. So we have good sources of X-rays. And what they would do is they would shine these X-rays onto atoms that have electrons. And what they would find is that the X-ray photon would collide with an electron and change its speed and change its position. And then they would do the little calculations on this, and it worked out perfectly in terms of their physics calculations. It's called Compton scattering. So essentially, what would happen, it's kind of cool. The photon would hit the electron, transfer momentum to it, so the electron's now moving faster. The X-ray would bounce back off, you know, just reflect off of it, right? But it lost some of its momentum by transferring it to the electron. And what happens is, and what's an X-ray? An X-ray is a photon. So it doesn't really have a velocity in terms of how we calculate it, but it has a wavelength. So the way it transfers its momentum is by changing its wavelength. Now, our perception of wavelength is color, right? So essentially what it does is it changes color. So the X-ray hits the electron's moving faster, the X-ray changes its color. So that's very good evidence that we can actually see this dynamic occurring of photons interacting with electrons.
Thank you.
Absolutely. All right, so let's take a look at quantum numbers. Very good. So we're not going to go through a lot of this. We're just going to look at sort of the general chemistry aspect of this. But essentially what comes out of this is the following. There's two things we've learned. One is that electrons behave like waves. So lambda equals h over mu. Right? That was the de Broglie equation from 6.3, I guess, or 6.4. And then we got the Heisenberg Uncertainty Principle, which says that, look, we really can't determine the position of something perfectly, of these electrons. For a car, you can, or a person, you can, but you can't really for anything that's microscopic. So what that means is we have to use a different analysis of the electron than the physics we use for rockets. So for physics for rockets are how fast it's moving, what's its position, how fast is the speed changing, which we call acceleration. That's how you deal with a rocket. That's how you deal with a bullet. And you can even deal with a person that way. But if we're dealing with electrons, we have to use a completely different physics. So we have to use what's called wave mechanics. Now, there's actually two types of physics that are used. Physicists use one type and chemists use the other. Oops, sorry. But they give you the same results. They have the same ability to predict the properties of these objects, of these things we call electrons, right? So this is the wave mechanics of electrons in an atom. And it's essentially predicated on the idea that you treat the electron as a wave. Now, the problem with this is that for the most part, even if you took all the courses in high school at the AP level, well, not the AP level. If you took AP physics, you would know a little bit of this. But most people even take, Regents physics, you don't know this stuff. Wave physics is quite a bit different from particle Newtonian physics. And so the analogy that I'll use are musical instruments. So musical instruments produce waves, right? Sound waves. And the way they do that is by vibrating. It's a vibration, essentially. So if you take a guitar string is very simple, right? You just take a string that's relatively has a high spring constant, and you pluck it. What'll happen is it'll vibrate between a minimum and a maximum. So it'll go back and forth, back and forth, back and forth. And as it does that, it will disturb the air around it. And it will cause the air around it to vibrate. And so the air will vibrate with a certain frequency, right? And so typically when you pluck a guitar string or a violin string, it will vibrate with more than one frequency. It will vibrate with what's called a fundamental frequency, but then it will vibrate with what are called overtones, which are multiples of the fundamental frequency. But essentially what we do is we treat the electron as the same kind of wave as the wave that's produced by a guitar string, and that's called a standing wave. A standing wave is what you get when a wave goes in one direction, but then goes back in the opposite direction as well. And those two directions, the waves will interact with each other to produce a wave that appears to not move. It's a very interesting type of wave. So you can also do the same thing with a drum. So a drum is the same idea. The difference between a drum is that it's 2 dimensions, right? So when you beat on a membrane, it vibrates, but it vibrates in 2 directions because it's a plane, so it's 2-dimensional. A string is 1-dimensional, right? So there's your string, there's your drum. So what happens out of this is that if you have a 1-dimensional vibration, you get what's called a quantum number out of it. And there's nothing particularly special about this. This comes out of the mathematics of guitars and violins. You get a quantum number, and the quantum number has certain values. Whole numbers, integer values starting at 1. So if you want to be able to analyze the vibration of a guitar, that's what you end up with, is essentially one result. You get this number, which corresponds to energy. Okay, so it's essentially the energy, but also the frequency. If you remember, for the photon, the energy of the photon was proportional to the frequency. That's true for waves. Okay, so if you do a 2-dimensional vibration, like a drum, then you get 2 quantum numbers. Okay, you get N, and you get L. And if you do 3-dimensional vibration, now there aren't very many 3-dimensional musical instruments out there. You get 3 quantum numbers. N is 1, 2, 3, 4, 5, 6, you know. L is 0, 1, 2, 3, 4, 5, ... And then M sub L is typically the symbol we use. 0, plus or minus 1, plus or minus 2. So this one takes on negative values also. So leaving aside the analogy of musical instruments, let's talk about the atom. The electron is a 3-dimensional particle, right? It can move horizontally, it can move into and out of the plane, and it can move up and down. So it's 3 dimensions. So a 3-dimensional vibration has 3 quantum numbers. So if we were 2-dimensional creatures, we would have X and we would have Y, but we wouldn't have Z. But we are 3-dimensional creatures, so we have the ability to go X, Y, and Z. Some people have postulated there may be 4-dimensional creatures which can do X, Y, Z and a 4th dimension. The same is true for the electron. The electron is in 3 dimensions, so it has 3 values, which are, they're not equal to X, Y, and Z, but essentially what we're claiming is that if it's 3-dimensional, it's going to have 3 values that describe its properties, and this would be these quantum numbers. So that's what we're going to use. We're going to use waves with these 3 quantum numbers to describe the properties of the electron. So 3 quantum numbers are used to describe the properties of an electron. There's actually a 4th that we'll look at later. It just has to do with the peculiarities of the electron. The electron being subatomic has a 4th property that we have to look at. Okay, so each electron in an atom has a specific and unique, meaning it's the only one that has that, set of values for these quantum numbers. Think of it like an address. Each apartment has its own specific address. It might be at 645 East 26, so that's one number, 645. It might be on the 4th floor, so that's a second number. And it might be in apartment D, that's the third number. But that each apartment has its own specific address. The same is true for each electron in an atom. Each one will have its own specific set of quantum numbers. So here are the quantum numbers. N is essentially the energy of the electron, how much energy it has. Now, if you go back to the earlier part of the chapter, remember when we said something like this, E equals minus R over N squared? See that N there? Now that N didn't come out of quantum mechanics. It came out of just looking at how to figure out what the wavelengths of light being emitted by the hydrogen atom were. So they came up with that. But it turns out that there's something deep in that N. It comes out to this. The reason they came up with that is because the electron's behaving like a wave. So it shows up over here. Okay. It can only take on values greater than 1. I'm sorry, greater than 0. It can't be 0. If it were 0, that would mean the electron has no energy. An electron has to have energy. Okay. And it can take on only specific values. Okay. The second one, L, is called, well, I'm not even going to give you the name. We're just going to say it's going to tell you the direction, not the direction, I'm sorry, the general shape of the space the electron occupies. Okay. And the values are 0 or 1 or 2 or 3 or 4. Again, this one can be 0. And it goes all the way up to n minus 1. So in other words, the maximum value that L can be is n minus 1. It can never be as large as n. So if I said n was 3, L cannot be 3. It could be 0, it could be 1, or it could be 2, but it cannot be greater than n minus 1, which would be 2 in that case. The third one, this one tells us the direction of space the electron occupies. Okay, so pretty trippy stuff. And the values here are 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. So it can't be any greater than L or any lower than minus L. But this one can take on negative values. So let me show you a little bit about notation here. What you're going to do with this is simple counting and notation. So the first notation I want to give you is L. If the value of L is 0 for the electron, we call that S. So if you see L equals 0, instantly you say S. And I'll talk about what S means in a little bit. If L is 1, you call that P. If L is 2, you call that D. And if L is 3, you call that F. Okay, so you're going to see both. You'll see L given as a number sometimes, but you'll also see it given as a letter. So if you see D, you should instantly translate that to L equals 2. Okay, so that's one aspect. The second notation that you want to be aware of is what's called orbital notation. So orbital notation, what you do here is you write n, you write the value of n, so you can actually give a number, and then you write the letter designation for L. So you're going to use a letter here. Okay, so for example, you might see 1s. If you see that notation, what you do is you say, okay, there's 1, so that means n equals 1. That's what the 1 means. So the value of n is shown first. So n equals 1. What that tells you is how much energy it has. That's the lowest possible energy level, n equals 1, right? The smallest you can get for n is 1, so that means it's the lowest energy it could be. And then you see an S, you say, oh, S, that means 0. So L equals 0. Okay, we'll talk more about what that means probably tomorrow. We'll get into what they mean tomorrow, but I just want to give you the notation right now. Here's another one. Suppose you see 4F. Okay. If you see 4F, well, that's telling you that n equals 4. And it's telling you that L is equal to 3, right? So that's telling you you're in essentially the 4th level. Okay, so you can think of it. We'll go just real quickly. I'll show you. N equals 1, n equals 2, n equals 3, n equals 4. This is energy, just like we did yesterday. We're doing this stuff so fast, right? 6 weeks is so fast to go through this stuff. But yesterday we talked about these energy levels, right? The energy levels in the atom. We still have those energy levels with quantum mechanics. In fact, quantum mechanics predicts these energy levels. So you have these energy levels. So if I say it's 4F, really what I'm saying is we're in the 4th level, right? So you're up pretty high in energy. That's pretty high up there. And we're also saying it's an F. That's telling us something about the shape of the space that the electron is occupying. And that's really fascinating. That's really what we're going to look at as chemists, is we're very interested in those shapes of space that we're taking a look there, okay? So let me just give you the names here. This n is called the principal quantum number, because when you do the Alex problem, they're going to give you the names of these quantum numbers and then ask you for the values of n and L. And then the second one is called the angular momentum quantum number. That's what L is. And then the third one is called the magnetic quantum number. That's M for magnetic. Okay. We have a 4th quantum number that we'll get into tomorrow. It's an important quantum number, and we'll take a look at that. But the first step in this is just being able to say, look, if I tell you it's 4F, what's the value of the principal quantum number, and what's the value of the angular momentum quantum number? Now, we only have a couple minutes here, but I want to show you a little bit about some of the limits on this. So let me save this one. I'm going to go over like a minute or two here just to show this to you. So sometimes what they'll do is they'll say something like this. Suppose they tell you that m sub L is equal to minus, well, let me put it this way. Let's just delete this. Suppose they tell you n is equal to 3. What are the possible values of L and m sub L? So part of this is just sort of arithmetic of these sequences. The mathematics this is sequencing, right? 1, 2, 3, 4, 5. And this goes all the way up to infinity, by the way. And then L is 0, 1, 2, 3, 4, but it can only go up to n minus 1. So this is setting a limit of how high you can go. And then m sub L also has a limit. It can only go all the way up to plus or minus L. So that's another limit. You can't go higher than that. Okay, so when it says what are the possible values of L and m sub L, what they're saying is what's the limit? How far can you go in these series of numbers? So here's how you do it. You take your n equals 3 and you say, okay, well, L goes all the way up. So go all the way up to n minus 1. N minus 1, so let's do L now. N minus 1, it would be 3 minus 1, right? That's 2. So that's your maximum. The maximum value you can go is 2. So what you do is you start at the beginning. You start 0, 1, 2, and then you stop, right? Because there's our maximum. So what that tells you is that there's 3 possible values of L. So if n equals 3, you could get 0 or 1 or 2. So 3 possible values. Now, going back to the previous problem, remember L has the symbols, SPDF. So that means it could be S or P or D, right? If L equals 0, that's S. If L equals 1, that's P. And if L equals 2, that's D. So that means if n equals 3, you could have S or P or D. Now, what about M sub L? Well, M sub L is 0 plus or minus 1 plus or minus 2 plus or minus 3, all the way up to plus or minus L. So let me do it this way. If L equals 0, then M sub L, it can only go up to plus or minus L. Plus or minus L is 0, right? If L equals 0, then plus or minus L is 0. So that means it can only be 0. There's only one possible value. What if L is equal to 1? Remember, we said that L could be 0, 1, or 2. Well, then M sub L could be 0 or plus or minus 1. Right? So now you got 3 values. 0, minus 1, and plus 1. So 3 possible values. Can't go up to plus or minus 2 because L is only 1. And then if L is equal to 2, here we go. We're going to stop at 2, right? You stop at whatever L is. So you stop at the 2. So here you got 5 values. 0, plus 1, minus 1, plus 2, and minus 2. Okay, so that's just the arithmetic of these quantum numbers. I haven't really given you much information about what they mean, except to say that as n gets larger, that's more energy. So think the electron has more energy in n equals 2 than it does in n equals 1. L is somehow talking about the space the electron is occupying, and we're going to call that an orbital tomorrow when we finish up this chapter. And then M sub L is somehow what direction this orbital is pointing. Is it pointing due north-south, or is it pointing east-west, or is it pointing towards you and away from you? It's somehow the direction of the space that these electrons are occupying. Okay. So there you go. I went a little bit over, sorry about that, but I wanted to make sure I got through that so that you can do some of those problems in ALEX. And then tomorrow what we'll do is we'll wrap up our discussion of these orbitals and do the electron configurations. And that right there will be the culmination of this chapter. We'll go everything from doing waves to now having a real definite answer to the electronic structure of the atom. And that will lead us into why and how atoms are able to bond with each other, how these electrons behave such that a hydrogen atom is attracted to an oxygen atom and you can form a bond between those two atoms and make your water molecule. Okay, so good. Have a great day. Reach out to me if you have any questions. I'll post this because this was some pretty interesting and different type of material. So if you want to watch parts of it again, and I did a couple of the ALEX problems, so that should help you out with your homework as well. So have a great day, everybody.
Thank you.
Bye. Thank you too.
Thank you.
Absolutely. Take care. Bye.
Have a nice day, Professor.
Thank you. Bye-bye.
Welcome. Bye.